Hello everyone, my name is Naina and I'm from the Budhi Academy. So now we will continue with the chapter that is hydrocarbons, and in today's video we will see the continuation of alkanes. Last time we have seen one chemical property of alkane, and that is halogenation, and today we will continue with the rest of the chemical properties of alkanes. Now amongst them, first one is the combustion. So we have already seen halogenation, how the reaction is and what is the mechanism. The next one is the combustion. The alkanes on heating in the presence of air or dioxygen are completely oxidized to carbon dioxide and water with the evolution of large amount of heat. So alkanes, when we heat them, when we heat them in presence of air means there is oxygen, right? So alkanes, when we heat them in presence of air or dioxygen, they are completely oxidized to carbon dioxide and water. So they completely gets converted into carbon dioxide and water, and in this process heat is evolved. For example, methane, when we heat it in presence of oxygen, it gets converted into carbon dioxide and water, and 890 kilojoules per moles of heat is released. This is in case of methane. What happens in case of ethane? In case of ethane, in presence of oxygen, carbon dioxide is released, water is also released, but the amount of energy that is released is 2875.84 kilojoules per moles. So the heat energy which is released in this process is more. Now the general combustion equation for any alkane is, this is the general combustion equation. In general, how you can do it. So it will be CnH2n plus 2. This is the general formula of alkanes. O2, how many O2 will be required is 3 multiplied by n plus 1 divided by 2. This much amount of oxygen will give you n number of carbon dioxide and n plus 1 number of water molecules, and what is released? Heat is released. Now due to the evolution of large amount of heat during combustion, alkanes are used as fuels. Since there is large amount of heat which is released during combustion, that's why alkanes are used as fuels. Now during the incomplete combustion of alkanes with insufficient amount of air or dioxygen, carbon black is formed, which is used in the manufacture of ink, printer ink, black pigments and filters. So when you have incomplete combustion means whenever alkane is not completely burned. In that condition, sufficient amount of air or dioxygen, this can occur because there is insufficient amount of air or dioxygen. In that case, carbon black is formed. And this carbon black can be used in manufacture of ink, or you can use it as printer ink, or it can be used as a black pigment and as filters. Now next, how that carbon black is formed. So first, methane, you have reacted with oxygen. Incomplete combustion means the methane is not entirely converted into carbon dioxide, so there remains a carbon which is solid, and H2O is formed. So this is the reaction for the formation of carbon black. This is the reaction given for the formation of carbon black. Now, controlled oxidation. Alkanes on heating with regulated supply of dioxygen or air at high pressure and in the presence of suitable catalyst give a variety of oxidation products. Now when you have controlled oxygen, when you can control the oxidation process, now in that case, alkanes, when you heat them with regulated supply of dioxygen, regulated supply means sufficient amount of oxygen is supplied, or air at high pressure and in the presence of suitable catalyst. When you give appropriate amount of air or dioxygen and with a suitable catalyst, you can get a variety of oxidation product. For example, methane in presence of appropriate oxygen and a catalyst, and here the catalyst is copper. Temperature maintained is 523 kelvins and 100 atmospheric pressure is applied. In this case you get methanol. Okay, it is methanol, that is an alcohol. But if same methane, when I react with oxygen, I just change the catalyst from copper to molybdenum trioxide, okay, dimolybdenum trioxide, and heat it. In this case you will get an aldehyde, that is your methanol. In place of methanol you will get a methanol. So alkenes, you can control the process, okay, you can give appropriate amount of air and a suitable catalyst can convert your product, same reactant, into different products. Okay, now this is ethane. Ethane with carboxylic manganese can give you ethanoic acid. Okay, now ordinarily alkanes resist oxidation, but alkanes having tertiary hydrogen atom can be oxidized to corresponding alcohols by potassium permanganate. Normally alkanes can resist oxidation, but the alkanes having a tertiary hydrogen means only one hydrogen which is remaining, other all are your bulky groups. For example, this here you have CH3, CH3, CH3 and one hydrogen. So in this case this hydrogen can be easily oxidized to a corresponding alcohol using potassium permanganate. Okay, so you will get an 2-methyl propantool. Okay, so this is what you get. So you can convert it into alcohol. The next is isomerization. Now, an alkanes on heating in the presence of a anhydrous aluminum chloride and hydrogen chloride gas isomerize to branched chain alkenes. Now a major product are given below. Some minor products are also possible which you can think over. Now minor products are generally not reported in organic reactions. Now isomerization means it is when you heat n number of alkanes. N number of alkanes means many number of alkanes when you heat them in presence of anhydrous aluminum chloride. Okay, this catalyst you have to remember: anhydrous aluminum chloride and hydrogen chloride, that is your HCl, hydrochloric acid. So in presence of hydrochloric acid and anhydrous aluminum chloride, when you heat n number of alkenes, you get an isomerized to branched chain alkenes. You get a straight chain to a branched chain alkenes. Now major products are given below. In this condition you get two products, one major and one minor product. Now major products we usually write. In organic reactions, minor products we generally do not report. We report all the major products. Okay, so this is one example. Here N-hexane, many number of hexane molecules are reacted in presence of anhydrous aluminum chloride and hydrochloric acid. What you get is two products. Okay, first one is 2-methyl pentane and second one is 3-methyl pentane. Okay, these are the two major products. Next is aromatization. Now N-alkanes having 6 or more carbon atoms on heating to 773 Kelvin at 10 to 20 atmospheric pressure in the presence of oxides of vanadium, molybdenum or chromium supported over alumina get dehydrogenated and cyclized to benzene and its homologues. Now what does this mean? You have N-alkanes of 6 or more carbon atoms. Okay, when you have an alkane chain of 6 or more than 6 atoms, when you heat it at 773 Kelvin and 110 to 20 773 Kelvin, and you maintain atmospheric pressure at 10 to 20, and this reaction takes place in presence of vanadium oxides, molybdenum or chromium. Okay, it can be either chromium, vanadium or molybdenum. Either the presence of these three any one, okay, either vanadium, molybdenum or chromium, any one of them supported over alumina get dehydrogenated and crystallize the benzene and its homologues. This reaction is known as aromatization or reforming. So here what happens, this is a 1 2 3 4 5 6 membered ring. This is an hexane. Okay, this hexane, what happens is when you react this hexane either in the presence of chromium trioxide, vanadium pentoxide or molybdenum trioxide, any one of them, and the temperature should be 773 Kelvin and at a 10 to 20 atmospheric pressure, this compound gets converted into benzene. So when you convert a compound into benzene, an aliphatic compound into benzene, it is known as aromatization because this is an aromatic compound. Now toluene is methyl derivative of benzene. So toluene, you know, it is a methyl derivative when you have benzene ring and you attach a CH3 group to that. So this is a toluene. So toluene is a methyl derivative of benzene. The next one is reaction with steam. What happens when you react alkanes with steam? Now methane reacts with steam at 1273 Kelvin. Now in the presence of nickel catalyst to form carbon monoxide and dihydrogen. Now, this method is used for industrial preparation of dihydrogen gas. So when you react methane, okay, when you react methane or alkane with steam, okay, the temperature will be 1273 Kelvin. So this will be the temperature. Now at this temperature, in presence of nickel catalyst, okay, you can form carbon monoxide and dihydrogen. Okay, you will get carbon monoxide and dihydrogen. Now, this method is usually used in industries where dihydrogen gas is prepared. Okay, the next process is pyrolysis. Now, higher alkanes on heating to higher temperature decompose into lower alkanes or alkenes, etc. So when you have a higher alkanes, okay, when you heat it, the temperature decomposes into lower alkanes or alkenes. Now such decomposition reaction into smaller fragments by application of heat is called pyrolysis or cracking. So when you take an alkane and you heat it to decompose means you separate it into two molecules, okay, which are either which can be a lower alkane or an alkene. Okay, this decomposition process is known as pyrolysis or cracking. For example, C6H14, this is an hexane. Now this hexane, you can break them into this many components. Okay, so hexane, either you can get an hexyl group and an H2 gas will be released, or when you heat it you can get an C4H8. What is C4H8? This is an butyl group, or C2H6, this is an ethane group. You can get an hexene, you can get an hexene, you can get an butene, you can get an ethane, or you will get C3H6. Okay, so you get propene, you will get an ethene, and you will get a methane. Okay, so you can get various products from one single alkene. Now pyrolysis of alkanes is believed to be a free radical reaction. Preparation of oil, gas or petrol gas from kerosene oil or petrol involves the principle of pyrolysis. So pyrolysis of alkane, okay, when you split or decompose an alkane, it is believed to be a free radical reaction. Free radical reaction means you get a free ion, okay, we get an electron to that. Now preparation of oil gas or petrol gas from kerosene oil or petrol involves the principle of pyrolysis. So when you prepare an oil gas or petrol gas from kerosene oil or petrol, okay, it involves the principle of pyrolysis. That means you are breaking it. Now for example, dodecane, a constituent of kerosene oil on heating. Dodecane means carbon 12. Okay, when you have a dodecane, where a constituent kerosene oil on heating to 973 Kelvin in the presence of platinum, palladium or nickel gives mixture of heptane and pentene. So when you have a dodecane, okay, when you react it at 9, when you heat it at 973 Kelvin in presence of either one of the catalyst, it can be platinum, palladium or nickel, any one of the catalyst, the product you get is an heptane and pentene, and there are other products also. Okay, so this is what pyrolysis is. Next is conformations. Okay, what type of conformations are there? Now alkanes contain carbon-carbon sigma bonds. Yes or no? Alkanes basically they are formed of single bonds, so they contain carbon-carbon single bonds, that is a sigma bond. Now electron distribution of the sigma molecular orbital is symmetrical around the internuclear axis of the carbon-carbon bond, which is not disturbed due to rotation about its axis. So when you have electron distribution of the sigma molecular orbital, it is symmetrical, right? Sigma means you are sharing the electrons. So on both the molecules, both the atoms will have equal number of electrons. Now, in the internuclear axis of carbon-carbon bond, which is not disturbed due to rotation of its axis. Now, this permits free rotation of carbon-carbon single bond. So, this eventually permits you to rotate the carbon-carbon single bond in any form. Now, this rotation results into different spatial arrangements of atom in space, which can change into one another. So, since the carbon-carbon single bond it is equally shared, you can arrange them in any format. You can put one on top, one on below. You can put them in any eggshell arrangements. Okay, so this rotation they result into different or spatial arrangements of atom in space, which can change into one another. Okay, now such spatial arrangements of atoms which can be converted into one another by rotation around a CC single bond are called conformations. Okay, when you have any spatial arrangement of atoms, okay, which can be converted into one another by rotation of that CC single bond, is called conformations or conformers or rotamers. Okay, now rotamers mean because you are just rotating it. Now alkenes can thus have infinite number of conformations by rotation around CC single bond. So whenever you have a CC single bond, you rotate them in any angle, you can have infinite number of conformations by rotations. Now, however, it may be remembered that rotation around a CC single bond is not completely free. Okay, whenever you have a CC single bond, it is not completely free. It is hindered by a small energy barrier of 1 to 20 kilojoules per mole due to weak repulsive interaction between the adjacent bonds. So whenever you rotate, okay, it is not like it is smoothly rotating. There is certain repulsion which is faced. Okay, there will be repulsion between the adjacent bonds, and that repulsion is 1 to 20 kilojoules per mole, not more than that. So that's why it doesn't affect that much, but there is still something small energy barrier to the rotation. Now such a type of repulsive interaction is called torsional strain. Okay, this 1 to 20 kilojoules per moles the repulsion which is faced, okay, that is called as torsional strain. Now let's see the conformations of ethane. Now ethane molecule, that is C2H6, contain a carbon-carbon single bond with each carbon atom attached to 3 hydrogen atoms. As you know, because you have 2 carbons and 6 hydrogens, so each carbon will get 3 hydrogens. Now considering the ball and stick model of ethane, keep one carbon atom stationary and rotate the other carbon atom around the C axis. This rotation results into infinite number of spatial arrangements of arrangement of hydrogen atom attached to one carbon atom with respect to the hydrogen atoms attached to the other carbon atom. So what they are trying to say is, you have two carbon molecules. Okay, one carbon molecule has hydrogens in, and second carbon molecule has this type of hydrogen. Okay, these are two carbon atoms. Now, what they want to do, they exactly trying to say is, okay, I'll put this one hydrogen in a red color so that you can make out the difference. So what they said is, keep one carbon as it is. Okay, this one carbon I'll keep it as it is with the hydrogens attached to it. The other carbon, they want us to rotate it. Okay, when we rotate the other carbon, okay, when we rotate the other carbon, this is what will happen. The hydrogen which was initially below, it will go on top, so it will change the arrangements. Now this can give you, now this rotation results into infinite number of spatial arrangements of hydrogen. So you can rotate it in any way, you can get a different or many types of carbon hydrogen spatial arrangements with respect to hydrogen atoms attached to the carbon atom. Now, these are called conformational isomers or conformers. So these type of structures, they are called as conformational isomers or conformers. Now, thus there are infinite number of conformations of ethane. Now however, there are two extreme cases. One such conformation in which hydrogen atom attached to two carbon are as close together as possible is called eclipsed conformation, and the other in which hydrogens are as far apart as possible is known as staggered conformations. Now since you can get n number of or infinite number of conformations of ethane, however there are two extreme cases. Okay, now in such cases, the conformation of hydrogen atoms attached to two carbon are close together as possible. Okay, when you rotate this, you tend to get two hydrogen close to each other. When this hydrogen come close to each other, they are called as eclipsed conformation. Okay, and the other in which hydrogens are far apart from each other, and the other conformation where you rotate it and you bring the hydrogen far away from each other, that is known as staggered conformation. Okay, now any other intermediate conformation is called skew conformation. So once you have hydrogen close, you call this eclipsed. When they are far apart, you call them staggered. But what if they are at equal position, or the intermediate ones, in between ones, close, far, there are in between period, no? So those intermediate conformations are called skew conformations. Now it may be remembered that in all the conformations, the bond angles and the bond length remain same. So in all this conformation, however far, however close they are, one thing never changes, that is their bond angle and their bond length. It remains same. Now eclipsed and the staggered conformations can be represented as Sawhorse and Newman projection. So by using Sawhorse and Newman projection, you can show eclipsed and staggered conformation. Okay, so let's see first Sawhorse projections. Okay, now in this projection, the molecule is viewed along the molecular axis. Okay, here you will see it along the molecular axis. Now what is the molecular axis? Your z axis is considered to be your molecular axis. Now it is then projected on paper by drawing a central CC bond as a somewhat longer straight line. So in Sawhorse projection, okay, there is a 3D model in which you will take the CC bond and you will arrange them in such a way that the carbon-carbon bond, when you show it on a paper, on a 2D model, you will show carbon-carbon long chain okay, somewhat long and straight line. Now, upper end of the line is slightly tilted towards the right or left hand side, so you can get a slightly tilted line, not a straight line, you get a tilted line like this. Okay, now the front carbon is shown at the lower end of the line, whereas the rear carbon is shown at the upper end. So this front carbon is your first carbon, which is close towards you, and rear means the one which is behind that carbon is shown at the second end. Okay, now each carbon has 3 lines attached to it corresponding to their hydrogen atom. Now each line you will be showing your hydrogen atoms. So 1 2 3, 1 2 3. Okay, these are same. You have something like this structure of hydrogens on both the ends. Now another way is again same thing. First carbon I am keeping it as it is, second carbon I am rotating it. So once I rotate it, it will become something like this. You get a Y shape. So in front you have an inverted Y and behind you have a normal Y. Okay, now this is what Sawhorse projection of ethane is. Now Sawhorse projection of eclipsed and staggered conformation of ethane are depicted here. This is the eclipsed one. Eclipsed means here both the carbons are parallel to each, all the 3 hydrogens are parallel to each other. They are close, right? They are close to each other. They are covering each other in the same pattern, right? This hydrogen is in front of this hydrogen, this hydrogen is in front of this hydrogen, this hydrogen is in front of this hydrogen. So they are eclipsed. You know what an eclipse is, right? They are covering each other. Whereas this is the staggered form where there is no covering taking place. Okay, so this is the staggered form and this is the eclipsed form. Next is a Newman projections. Now in this projection the molecule is viewed at the carbon-carbon single bond head on. Now the carbon atom nearer the eye is represented by a point. Now 3 hydrogen atoms attached to the front carbon atom are shown by 3 lines drawn at an angle of 120 degree to each other. Now in Newman projection you have a carbon-carbon single bond head on. Now the carbon atom nearer the eye is represented by a point. Okay, the 3 hydrogen atoms attached to the front carbon atom are shown by 3 lines drawn at the angle of 120 degree. So here you will only show one carbon, the carbon which you see from the front. Okay, here how you showed 2 carbons. In Newman projection you will show only one carbon in the form of a dot. Okay, and the hydrogens you will show them in the form of lines. Okay, and the angle between them will be 120 degree to each other. Now the rarer carbon atom, the carbon atom away from the eye, is represented by a circle and the 3 hydrogen atoms are shown attached to it by a shorter line drawn at an angle of 120 degree to each other. Now this dot, okay, this dot is the one which is in front and this circle which is behind is the carbon which is behind that carbon. For example, carbon 1 and carbon 2. Now this dot is what your carbon 1 is and this circle is what your carbon 2 is. Okay, and the lines show these blue lines show the hydrogens which are attached to the carbon 2. This is what Newman projection is. Okay, this is the eclipsed one where hydrogens are close to each other, and this is staggered one where hydrogens are far away from each other. Now the angle of rotation or angle of torsion or dihedral angle. So this angle between this hydrogen and this hydrogen, this angle is called as angle of torsion or angle of rotation. Next is the relative stability of conformations. Now, as mentioned earlier, in staggered form of ethane, the electron clouds of carbon-hydrogen bonds are far apart as possible. So, as mentioned earlier, in staggered form, you know that hydrogens or electron cloud of carbon-hydrogen bonds are far apart as possible. Thus, there are minimum repulsive forces, minimum energy and maximum stability of the molecule. So, staggered form of ethane, they show relatively high stability because there is minimum repulsive force because all the carbon hydrogens are far away from each other. So there is minimum energy and maximum stability. Now on the other hand, when the staggered form changes into an eclipsed form, the electron cloud of the carbon hydrogen bond come closer to each other, resulting in increase in the electron cloud repulsions. So when you have staggered form, when you convert staggered form into eclipsed form, in that case what happens, your carbon hydrogen bond which is there, it come closer to each other, and this results in the increase in electron cloud repulsion. So to check the increased repulsive forces, molecule will have to possess more energy, thus lesser stability. So this repulsion will lead to more energy requirement and thus the stability is decreased. Now, as already mentioned, the repulsive interaction between the electron clouds which affects stability of a conformation is called torsional strain. So already we have seen what torsional strain is. So it is the repulsive interaction between electron clouds which affects the stability of the conformation is called as torsional strain. Now, the magnitude of torsional strain depends upon the angle of rotation of CC bond. Now, torsional strain, it basically depends upon the angle of rotation of carbon-carbon bond. Now, this angle is also called dihedral angle or torsional angle. So, this is called as dihedral angle. Dihedral angle means you have a dihedral structure or a torsional angle. Here I have shown you what is a dihedral. See, this angle, this angle is called as, for that matter, this angle, this angle is called as angle of rotation, angle of torsion or dihedral angle. So, of all the conformations of ethane, the staggered form has the least torsional strain and eclipsed form has the maximum torsional strain. So, of all the conformations we see in that of ethane, the staggered one has the less torsional strain, whereas the maximum torsional strain is seen by eclipsed form. And therefore, the staggered conformation is more stable than the eclipsed conformation. So, because of this, staggered is more stable than eclipsed. Now, hence, molecule largely remains in staggered conformation, or we can say that it is preferred conformation. So, since staggered is more stable, we prefer staggered over any other conformation. Thus, it may be inferred that rotation around CC bond in ethane is not completely free. So when you have thus it may be inferred that the rotation around CC in ethane is not completely free. There is some kind of repulsive force which is taking place. Now the energy difference between the two extreme forms is of the order of 12.5 kilojoules per mole, which is very small. So the energy difference between two extreme forms of the order, it is called as 12.5 kilojoules per mole, which is a very small amount. Now, even at ordinary temperatures, the ethane molecule gains thermal or kinetic energy sufficient enough to overcome this energy barrier of 12.5 kilojoules per mole through intermolecular collisions. So even in ordinary temperature, in normal temperature, room temperatures, ethane molecule can gain thermal or kinetic energy, and this gain of thermal or kinetic energy is sufficient enough to overcome the energy barrier of 12.5 kilojoules per mole. That's why ethane can rotate easily through intermolecular collisions. Now, thus, it can be said that rotation about carbon-carbon single bond in ethane is almost free for all practical purposes. So in this way, the carbon-carbon single bond in ethane is almost free for all practical purpose, because whatever torsional strain it experiences, that torsional strain can be reduced by intermolecular collisions. Okay, so eventually it gets zero. Now it has not been possible to separate and isolate different conformational isomers of ethane. So it has been not possible. Okay, it is very difficult to separate and isolate different conformational isomers of ethane because they have relatively same size and properties. So this is what alkenes are. So here we have completed alkenes. In our next video we will see about alkenes. So thank you for watching our video. Please do like, share and subscribe to our channel.